Hello, my name is Logan Harvell. I am a game developer and a graduate student currently enrolled in the master's program at UCF's Florida Interactive Entertainment Academy. In this video, I'll be going over the Fiea game engine, a personal project that I have been working on since early 2020. It is a property-centric and data-driven game engine that currently supports both Windows and Linux projects using Visual Studio. It is being developed in C++. And what you're looking at right now is a solar system demo that goes and shows off some of the aspects of the game engine, notably the hierarchically structured game objects, as well as what you can't see, which is the data-driven nature. The entire solar system demo itself is controlled using JSON configuration files that can be hot reloaded to change the actual nature of the demo. And the whole solar system itself is actually populated using JSON. But without further ado, I will go deeper into the actual game engine itself so that we can look at what the engine is capable of and how it's been designed. To begin, let's discuss the entity system. It forms the fundamental system within the engine. Specifically, the entity class defines a basic game object, and it is the singular base class from which all other game objects are derived. We have a world and actor class that derive from entity, as well as a number of action classes that derive from it as well. And the user can define their own classes that derive from entity to create their own game objects. Like in the demo, you saw the planets were all derived from actor and defined a solar body class with their own set of properties. But to explain exactly how the hierarchical structure was established for game objects, we have to discuss entity a little further. Each entity is capable of having one or more children entities contained within it. These children entities are full entities of their own right and can have one or more of their own children. And these children don't actually have to be just simply entities themselves. They can be any derived entity class. And this is how we were able to create the solar system of solar bodies. However, there needs to be some root level entity that manages the state and resources of the game. And this is where the world class comes into play. It contains a world state, which is a data structure that is used to pass down the state of the game through the ownership hierarchy. The world class also contains the methods for managing the game loop, specifically the run, update, and stop methods. Now, because world is also an entity, it is obviously capable of having one or more children entities. And you can consider these top-level entity objects within the world almost like a level. These top-level game objects can then be added or removed, just like you would load or unload a level from a game. In the case of the solar system demo, we had a world, and it contained a solar system as the root level entity, making the solar system the level, and all of the solar bodies it contained the game objects within it. Now, we've mentioned the actor class, and that it has its own transforms. However, we haven't actually discussed the implementation. So, actor contains actually two transforms, a local transform and a world transform, where the local transform describes its relative location and orientation in local space, and the world transform describes the overall orientation and location in world space. But what actually makes up a transform? Well, a transform can be broken down into three main components: translation, rotation, and scale. By maintaining these as separate components within the transform class, namely two vectors and a quaternion, we are able to have easy access to each component without requiring matrix decomposition. Additionally, simple transformations along only one of these components only requires basic vector arithmetic, preventing unnecessary matrix multiplication. And the implementation within the game engine goes actually one step further and caches the most recent matrix composition so that you don't have to recalculate it when there have not been any intermediary transformations. So now that we've covered the core system behind the engine, I think we actually should dive to the bottom. At the most basic level, this engine relies on foundational container classes, of which there are 3. Each of these was designed after the standard template library, and they include slist, a singly linked list class, as well as vector, a dynamic array, and hashmap, a hash table with key data pairs. These classes are completely generic through C++ templates and are complete with iterators and move semantics. The engine also contains a stack class, which is just an adapter container that represents a last in, first out stack. However, that isn't the last container. There is one more, and it's actually a very exciting part of the engine, which is the datum class, which is a dynamic array very similar to vector. However, it is able to have its type defined at runtime. This is done through a set of pointers in a discriminated union so that they all share the same space in memory. Then when combined with a enumeration, you can set the type of the datum and treat it accordingly. Now that we've described the containers that form a foundation for many of the types inside of the game engine, we are capable of discussing the runtime type reflection system. This is the underlying system that allows us to have runtime defined entities, as well as entities that can be modified by JSON code. At the base level, we have a scope class. This is simply a wrapper class to a hash map of string keys mapped to datum instances, or more simply put, names with runtime definable types. We'll be calling these attributes. This class is then extended through the attributed class, which is an abstract base class derived from scope that's purpose is for registering and exposing attributes. Each derived class from attributed should provide a signatures method, which is a method that returns a list of signatures that describe any predefined attributes that the class type contains. And since datum is actually capable of containing references, not just internal types, we can use these signatures as references to data members found within a class. However, the real value of this reflection system comes into play when we start discussing data-driven development. So, how exactly do we do data-driven development? The answer is that we expose this reflection system to an outside source, namely our JSON parser, that when using this reflection system is capable of defining completely new entities as well as modifying pre-existing entities within a hierarchy using the references to their data members that the datum provides, since each entity is itself actually derived from attributed. The details of the implementation of this lie in the JSON entity parse helper. This is an implementation of JSON parse helper, which describes the step-by-step process in which you parse the key data pairs in JSON into an entity and its attributes. However, to support being able to create new entities within JSON, we have to be able to create any derived entity class using just a given identifier, like a class name. So to support this, the engine employs the abstract factory pattern, using a factory class that is capable of creating a class instance using that class name identifier. Naturally, this isn't actually a problem if all you're doing is parsing JSON into pre-existing entities, since all you're doing is retrieving that pre-existing entity given its name, or rather its key within the underlying scope. Bringing this all in together, this is what allows us to be able to take a JSON as a configuration file and then load a level completely from within JSON, such as the solar system. This is shown in the JSON here. However, we can take this even a step further, and by reparsing the JSON, we are capable of hot reloading the level, which I described briefly in the initial demo. Here's an example of hot reloading in action, where we increase the distance and timescale parameters of the solar system, as well as increase the diameter of the sun, and we add a number of different planets to the solar system, all during runtime. If you've managed to make it this far into the video, I really appreciate you taking the time to watch. I know there's a lot of material I had to kind of skip past, so if you'd like to hear more about some of the systems that I wasn't able to talk about here, feel free to check out my website, as well as the source code that can be found on GitHub, or if you'd like to discuss the project with me personally, feel free to reach out. Otherwise, if you'd like to follow along with my current work, I am in the process of developing a rendering abstraction layer so that I can define a single simple interface that is used to implement rendering APIs so that you can isolate dependencies on specific rendering API depending on the specific target platforms and the application being developed within the engine. This will allow for the engine to be extended with different implementations for various rendering APIs as desired. And if you'd like to follow the progress, make sure to visit my blog. Thanks again for watching, and I hope you guys have a wonderful day.